Hello, I'm Vincent Laporte, and on behalf of all my co-authors, I'm pleased to tell you about the last mile, high assurance and high-speed cryptographic implementations. In this work, we are interested in the building of cryptographic libraries that are both efficient and trustworthy. And in this context of cryptographic libraries, there are some specific goals. So we want the code to run extremely fast while being correct. And since these libraries are building blocks for security mechanisms, we want the implementation itself to be secure, that is to say, protected against side channel attacks. And also, we want to be able to provide formal guarantees that these libraries actually provide security. Unfortunately, these requirements are often seen as conflicting. So for instance, for protecting against side channel attacks, programmers rely on non-intuitive programming patterns like constant time programming. Also, for the sake of performance, the optimizations are heavily optimized, and this is error-prone and makes the code harder to formally verify. These challenges have been addressed independently by different communities. On the theoretical side, there are strong foundations in provable security and in freedom of leaks due to side channels. On the engineering side, there is a long practice for writing very efficient code and design patterns to protect against side channel attacks like constant time programming. On the formal verification side, there are works that establish the functional correctness and the absence of leak through side channel on actual implementations. Also, there is some recent efforts that deliver combined guarantees, but until recently, those works have often compromised on the efficiency of the final results. So in this work, we would like to deliver all the guarantees without any compromise. And to do so, we rely on two things: methodology and tooling. And at the heart of this work is Jasmine, a programming language in which the programmer can write very efficient code, and this code still can be formally verified. So together with the language, we provide a compiler that is certified, like the CompCert compiler. So we have a proof in Coq that it preserves the behaviors of the Jasmine programs. And also, the programmer has access to rich verification infrastructure that is based on EasyCrypt, and this enables to prove formal security of the implementations, but also their safety, their resistance against side channel attacks, and their functional correctness. Our work is supported by a few case studies. I will tell you about two TLS 1.3 components, ChaCha20 and Poly 1305, but there was this paper at CCS last year about the cryptographic security proof of an implementation of SHA-3 down to optimized assembly. And there is some very exciting ongoing work on primitives for post-quantum cryptography. So let me now give you a bit of taste of what the Jasmine language looks like. So this is extracted from an implementation of ChaCha20, which is a stream cipher which encrypts each block of a message by mixing it with a state. And this function here is responsible for initializing these states from a secret key, a nonce, and a counter. And what we can observe in this example is that the language provides a few high-level constructions like functions and loops to structure the code, and also arrays to structure the data. But the programmer has some control over some low-level details, So for instance, here, through this stack or register annotation, the programmer chooses where the data is going to be allocated. Also, the loops can be completely unrolled by the compiler. This is indicated by a for loop, or while loops will be preserved by the compiler. And complementarily, the programmer is given access to a few low-level features. So for instance, the programmer has direct access to the instructions of the underlying architecture. And on the case of x86, the programmer has explicit access to all the arithmetic flags as ordinary variables. And seeing these flags are usual variable makes the reasoning about the program much simpler. Also, the programmer has access to the SIMD extensions that enable vectorized processing, and when possible we provide a high-level syntax like this, denoting 8 parallel additions on 32-bit values. And the x86 architecture is very abundant in terms of instructions, and it will be extended in the future. So the compiler is organized in a way so that each instruction is compactly described by a single descriptor. And therefore, if we want to add support for a new instruction, what we have to do is only to describe this instruction in a single place, and we don't have to change the other places of the compiler, and in particular there is no need to change the proof when we add a new instruction. So this was for the language, and around the language is a rich verification infrastructure. At the heart of this infrastructure is the compiler. So it takes Jasmine source programs and produces corresponding assembly programs, and this compiler is certified. So like the ComCert compiler, we have a cock proof that the behaviors of the assembly program are the same as the behaviors of the source program. And therefore, this legitimates that we do formal reasoning at the source level. And this reasoning is done through the EasyCrypt proof assistant. So the Jasmine compiler can produce models of the Jasmine program for EasyCrypt, and these models can in turn be used to prove functional properties like functional correctness or cryptographic security, but also non-functional properties like constant time security. And all these formal proofs rely on the fact that the source program is actually safe. This is why the Jasmine compiler can also automatically check for safety. So this was for the tooling, but tooling alone is not enough to verify complex pieces of software. So let me now talk a bit about the methodology. So we start from a functional specification that is a high-level mathematical description of the intended behavior of our program. And on the other hand, we have highly optimized low-level implementation. And in practice, we may have several of these implementations that are optimized for different variant of the microarchitecture, or optimized for different sizes of the message. And what we want to do is to prove that these implementations are correct with respect to the specification. And we don't do this directly, but through a long series of small steps. And the first step here is to give a different view of the specification, to rewrite the specification as an imperative program. So this imperative program can be easily verified using usual OR logic against the functional specification, because it will be very close to the specification, and in particular it may manipulate ideal mathematical objects rather than low-level bit vectors. And then all the following steps are going to be justified by an equivalence check, because we are comparing two programs and we want to prove that they are equivalent. So by transitivity, when we end up here with our optimized implementation, we know it's equivalent to the imperative specification, which in turn is correct. And we go through a lot of small steps so that each step is only concerned by one particular aspect of the implementation. So for instance, here, this step replaces ideal mathematical objects by their bit level representation. And this kind of transformation is common to many cryptographic implementations. Therefore, this part of the proof can easily be reused for different implementation. So let me now zoom into the last hops of the correctness proof of ChaCha20. So this stream cipher applies a body of code to each block of the message to encrypt. And we want to prove this reference implementation equivalent to the optimized vectorized version. And we do so in 3 steps, in 3 hops. In the first hop, the loop is unrolled a bit so that at each loop iteration there are 4 blocks of the message that are processed. Then in the second hop, we reschedule the instructions of the 4 copies of the body to make explicit opportunities for vectorization. And this is what is done in the last hop, when we replace sequences of instructions by single vectorized instructions. And in this way, we can split the proof, and for instance, the last part is only concerned by the semantics of vectorized instructions. And I would like to mention that some of these proofs, and especially here the scheduling part, are simplified by the fact that in Jasmine the different arrays can never alias, and this provides a kind of separation logic for free. And in this proof we are concerned by proving that different instructions can be reordered because they are independent, and in this case separation logic is very useful. So to sum up on the verification infrastructure, we have a translation from Jasmine program to EasyCrypt that preserves the high-level abstraction and structure of the code to minimize the proof effort. And this allows to prove formal security of the implementation, but also we can use this to prove constant time security. And moreover, there is a safety checker that allows to check the program safety before doing verification. I mentioned in the beginning of this talk that we want to deliver very strong guarantees without compromise on the performance. So let's have a look at a few measurements. Here we report the time it takes to process a single byte of message depending on the total size of the message, and this for several implementations. And what we can observe is that the Jasmine implementation, like the black curve here, provides similar performances as the best handwritten assembly that is taken from OpenSSL. Also, if we focus on formally verified assembly codes, we can observe a few things. So here, for instances, these two curves correspond to the same code, but here compiled with Comcert and there compiled with Jasmine. And so what I would like to highlight is that using a verified compiler is not necessarily bad for performances, because in Jasmine the programmer has enough control on the assembly that is generated to avoid paying a penalty for using a certified compiler. And also, in this final graph, here we have three curves that correspond to assembly level programming. And these two are very close, and they actually use they correspond to scalar implementation. And here we have a gap in performance due to the use of vectorized instruction. So it's very important to have a language and compiler that is easy to extend to be able to use all the low-level features that are provided by the microarchitecture. So this brings me to the end of my talk. So I've shown you Jasmine, a language for implementing highly efficient cryptographic routines that comes with a certified compiler and a verification infrastructure that can be used to prove safety, side channel security, functional correctness, or even cryptographic security. There is a bit of ongoing and future work to first enrich the language, for instance with non-inline functions, to be able to write larger pieces of code. And we are also studying the connection with other safe languages like Rust, and there are more case studies to be done, and in particular in post-quantum cryptography. So thank you very much for your attention.